the two categories, because you don't need to. Do panic if you don't know what quantum information is, because you're in the wrong room. Right. Work. Okay, so the main idea underlying this work is that quantum information is a topological concept. This is something that was emphasized by Samson Abramsky and Bob Cooker, who, among other things, gave an elegant account of some part, at least, of quantum teleportation and what it means in terms of the topology of one-dimensional manifolds. The fact that quantum teleportation works is something to do with the fact that if you've got a piece of string with a little bend in it like this, pull it straight, then you just have the sort of single string with no points. And we can look at this bent string and we can understand why this has something to do with quantum teleportation. We read it going from the bottom to the top. At the bottom, we just have a single piece of string coming in. We interpret that as our quantum system. Then, going up vertically, we have a critical point here, and we have two new systems being created. And we interpret these as being in a Bell state, and they're entangled because they're connected by this piece of string. And then here, we have this little second bend, looking at our first and second quantum systems, and we interpret that as successfully measuring the joint state of the first and second quantum systems in the Bell state. And suppose we do that, so we perform this post-selected measurement. If that was successful, then indeed quantum teleportation tells us that we've successfully teleported our qubit. In other words, our quantum system has proceeded unchanged. Now, of course, quantum teleportation is a lot more than that, and Abramsky and Cooker certainly deal with all those issues. But this picture that comes out of their work is, I think, of profound importance. It's something that we need to take seriously, and we need to ask ourselves, what does it mean that quantum information is topological, and what can we do with that? Okay, so in this talk, I'm going to develop this sort of topological ideas in some significant ways. In particular, this topological picture, which here just accounted for one post-selected fragment of the quantum teleportation protocol, is going to be extended to the entire protocol, so regardless of the measurement outcome. Instead of a one categorical formalism, which Abramsky and Cooker use based on monoidal categories, we're going to switch to a two categorical syntax. So our mathematical machinery is going to ramp up one notch. And underneath it, we're going to have an explanatory model for what this two-category theory is doing in terms of information transfer and correlation between quantum systems, although that part of things won't really be emphasized in this talk. Okay, so to start, I'm going to talk about the notion of a formal algorithm. So to start with, what's a formal protocol? Well, a protocol is just something that we do, right? It's a list of instructions, it's a recipe to get these pieces out of our drawer, put them on our lab bench, and do these things. Right? Just a set of instructions. But for us, a formal protocol is going to be something that looks a bit different. It's just going to be a picture. It's going to be built out of regions, lines, vertices. Regions are going to represent classical information. Lines are going to represent quantum systems, and vertices are going to represent some sort of quantum dynamics, which could be anything from a measurement being performed, some sort of control operation, or all sorts of things. Now, a formal algorithm is going to be an equation between two such protocols, that is, an equality. In other words, that will mean if you do this particular set of things, that should be equal to doing this other set of things. And that's a slight generalization, perhaps, of how we think of a quantum algorithm, but it's certainly strictly a generalization, right? If we take something like teleportation, so we have got a picture that represents teleportation, it shouldn't be clear quite yet why that's got anything to do with teleportation, but we'll see that in a minute. Ordinary quantum teleportation says if we do these things, do a parallel state, do a measurement, perform a control operation, send some information, and so on. For that protocol, that should be the same as performing some other protocol, where Alice just puts her qubit into a sort of sealed sort of quantum box that can protect from decoherence, gives it Royal Mail or whatever they're called these days, and ships it over to Bob, right? So ordinary quantum And we're going to see that this picture, this formal algorithm, that is an equality between two formal protocols, captures that. We can do the same for lots of other familiar quantum algorithms. Those involving complementarity, dense coding, something that I call interlaced teleportation, which I'll talk about later on. So what's this got to do with two-category theory? Well, all that two-category theory is a sort of powerful algebraic setting where instead of ordinary algebra, where we can just compose things in a line, we can compose things on the plane. So we can put them next to each other or on top of one another. And it's precisely the right sort of mathematical toolkit to work with these sorts of things in an interesting way. So because of this fact, I can hide away the machinery of the two-category theory and I can just draw pictures. So that's what I'll do in this talk. And in fact, that should tell you that really, if you feel you've got a good geometrical intuition, two-category theory really isn't very scary. In fact, it's very beautiful. Serves as a wonderful way to organise these sorts of diagrams. Okay, so how can we interpret these pictures that I've been drawing? Well, they're built up from quite a small number of components. We can just go through them one by one. So the first and most important component is performing a measurement. So all of these little fragments we're going to read from bottom to top. So when we perform a measurement, we start with a single quantum system. It's our single line. And then something happens. We've got this black blob. Then at the end, we've got two quantum systems. There's one on the right and one on the left, linked by some sort of non-trivial region. Remember I said regions represent classical information. So what's going on here? Well, we started with one quantum system. We've ended up with two. And those two quantum systems are correlated with respect to some classical information. What does this mean? Why does this make sense? Well, all that classical information is, from this perspective, correlations between quantum systems. So we're going to need at least two quantum systems, or we can't talk about the existence of correlations. And if you like, this red region can be thought of as sort of a future light code, or future information code of our measurement, containing an unbounded number of copies of our quantum system. And if we want to know what the result of our measurement was, I can just extract one of those copies out and send it to somebody. And this sort of red region hides all this classical information inside. Now, for me, this is a unitary process. Right? There's no decoherence necessarily, because I'm keeping track of all the correlated entities that are resulting from my measurement operation. So in principle, I can undo my classical correlations. I can simply do the converse. So this is formally part of the scheme. What would that mean in reality? Well, it would mean that anything that's correlated to the measurement outcome that you got, the photons that bounced off your lab book when you wrote your outcome and so on, you'd have to capture all of them and perform some big unitary operation to revert things to how they were. So physically, there's nothing really wrong with that. Maybe you say physically it doesn't make much sense, but that's fine, you just don't make use of this component. But the point of putting these both here is to show that a measurement is a completely unitary process in this scheme, right? And these two operations are inverse to each other. So what else can we do? Well, I described that these shaded regions can be thought of as an unlimited supply of copies of our classical information, so certainly we can extract a copy. So this is an operation where we obtain a new quantum system coming out of our classical region, a quantum system we didn't have before, and that will be instantiated in some pure state, which will just represent the particular value that our classical data has. So say that we've got some two-dimensional piece of classical data just storing a bit, then this new quantum system that's branching off will be in the pure state 0 or pure state 1, computational basis, say. And similarly, we can do the converse of that, the adjunct of that. We can compare some quantum data, the state of some system, with some classical data. And in general, that will be a post-selecting operation. So it will sort of, when we see that, that means we do this comparison, and the comparison is successful. Yeah, sure.
Maybe you're going to come to it, but why is the red region just to the left of that line? Why doesn't it spill over when you copy? If it's taking with it.
So this is just a tiny little fragment of our picture. Well, later we'll see some protocols in their entirety, and then hopefully the scope of the classical information will make good sense. We can ask the question later. So what else can we? Yeah, sure.
So the rule to read the graphs from bottom to top is, it applies to the previous one.
It's to everything, and it's fixed. But having said that, we can also move things around however you like. So actually it's not a limitation. So we'll see how that works in a precise time. So what else can we do? Well, if we've got some classical information in this red region, we can copy it. We can end up with two regions of classical information. And those will hold a piece of classical information which is just a copy of the piece of classical information we started with. Or again, we can do the converse. If we've got two regions of classical information, we can compare them and ensure they're the same. Again, we interpret this in a post-selective sort of way. Right? So if you want to describe protocols that don't involve post-selection, well then you can't use this fragment, because this fragment insists that two regions hold the same data. A few more things we can do. We can create some uniform classical data. So how could we understand this? Well, if our quantum data, if our classical data, is just a single bit, 0 or 1, then we could prepare a qubit in the state 0 plus 1, and then we can measure it on a computational basis. And that's just what we mean, really. That's what I mean exactly by creating uniform classical data. We represent this naturally in this fragment. Similarly, we can forget our classical data. We can throw away our notebooks. Really, the operation of throwing away your notebook isn't entirely right, because if you did that, still copy of the information that's in your notebook would be somewhere in the environment. You get the idea. And now finally, we get the most important part of the formalism, which is performing a controlled operation. Now this involves a system here on the left, which is correlated with respect to some classical information. So we can consider that as encoding our classical information. And a quantum system, which isn't correlated with anything at all, that's just in some pure state, interacting in a non-trivial way. And this means exactly performing a controlled operation. So we could do nothing, if we liked, or we could just do some given thing to the quantum system, and we could ignore the classical information, or, in the most general case, we could do something to the quantum system depending on the value of the classical information. And that's what this is.
Is it a unitary operation or not?
If you like, or it can have a kernel if you want. A kernel would mean I'd post-select in the case that my state is this kernel, but sure. If we could talk about teleportation, say that this would be a unitary operation. Now, coming back to a question that was just asked a few moments ago, if the diagrams for any two protocols are homotopic, we can stretch and bend one to turn it into another, with respect to some fixed boundary, right? So where things go up to the top and bottom or left and right of the diagram, we can't change that. But if we can squeeze or stretch one diagram to another, then we consider them to be equal. And it means they'll give rise to exactly the same quantum information flow. So, for example, here we've introduced this little kink. Before, this was just a smooth system remaining unchanged, correlated to classical information. And now we're doing something different. We're creating uniform classical information here, so we've got two regions of classical information, and then we're post-selecting for the case that they're the same. That's the same as the original piece of classical information we had. And clearly that's the same as just doing nothing with the classical information. And the fact that you can stretch and bend your protocols however you like to get something different, physically different in the sense that it corresponds to different action in the laboratory, but encoding exactly the same flow of quantum information, is just a manifestation of the topological nature of quantum information. That's what we mean. This is one thing that we could mean by a statement that quantum information is topological. So what about implementation? Everything we've been talking about so far is formal, it's just pictures. It's about quantum mechanics, it's about linear algebra, it's about all this based. Well, for me, to implement a formal algorithm that is conform with quality between two pictures is to find a solution for it. Remember, it's an equation, right? So quality between two things. We want to find a solution for it. But what do we want to find a solution in? Well, not a solution out of a field or something, a solution in a particular two categories. Because these are diagrams, these are equations among two cells in two categories. Now, so whether or not you can find an implementation will depend on the target that you pick. This is still an abstract concept, particularly quantum mechanics as yet. If you pick your target, then certainly not all formal algorithms will be implementable. You won't always be able to find a solution. And whether or not you can depends entirely on the sort of target that you pick. Of course, we're interested in standard quantum physics. We're interested to say, suppose we've got some formal algorithm described in these terms. When can I implement it in ordinary quantum theory? And for us, that exactly means finding a solution for it in a 2 category called 2-hill, which has been studied already in the literature. It's due to John Bayes. So I'm going to very quickly talk about what this looks like, and we'll see it in a more friendly way in a few slides' time. So our regions are essentially Hilbert spaces equipped with a chosen basis. They're classical structures, they're Dagger-Frobenius algebras, if you like, if you're interested in that, if you know about that sort of thing. So if our classical information is just a single bit, then we would choose the copying operation on C2, which just copies the computational basis. That's what our regions are. Our lines are just Hilbert spaces, but they're equipped with actions of the Frobenius algebras on each side. That is, if you pick a particular value for the classical information on the left and right of our system, that gives you a projector onto your quantum system, saying, this is the value of the classical information, so my quantum state must lie in this subspace. Composition of systems, putting systems next to each other like this, is a sort of fiber tensor product. So the idea is we take the tensor product of the Hilbert spaces of our systems, but then we throw away all the parts of that tensor product where they disagree on the value of certain classical information. And then finally, linear maps and linear maps which preserve all this structure. So this is a bit messy, and this is all I want to say. Well, it's actually beautiful and everything, but it might look a bit messy if you're not familiar with modules and actions and so on. Really, it's a very natural notion. Certainly been studied an awful lot in the past for all sorts of different reasons. And it turns out to be perfect for what we want to do, talking about implementing our formal algorithms. Okay, so now we're going to talk about impossible algorithms. An impossible algorithm is a formal algorithm, it's an equation between these pictures, which has no implementation in quantum mechanics. So it has no solution in this 2 category we just described, 2 Hilbert spaces. Now sometimes our quantum information is enough to tell us why that should be. So here's an example of an impossible algorithm. Let's unpack what this algorithm says. So here, on this more complicated left-hand side, we start with some classical information. This is some quantum system that's correlated with some classical information. And a quantum system here that's uncorrelated. Then we introduce 2 more quantum systems here, which are linked by a wire, so that means they're in a Bell state. So now we've got 4 systems, our original qubit, 2 systems which are entangled with each other, and a 3rd system that represents the value of some classical information. And then we're going to do 2 things at the same time. We're going to measure our first 2 systems in some bipartite basis. And we're also going to perform a control operation on our 3rd qubit, depending on the value of this classical information. And then that's it, and we're done. What does the right-hand protocol say? It says we leave our initial system completely unaffected. We do absolutely nothing with this piece of classical information we've got here, and then we just uniformly generate this new red piece of classical information. Now, if you think about what this means in terms of quantum mechanics, I mean, there's just no way that this should be possible, right? Because here, your quantum system, you're measuring your quantum system and correlating it with this piece of, you're getting some classical information about it, which is correlated to it. But then your quantum system never interacts again with this region. So there's no way to undo that correlation. So in quantum teleportation, we do a measurement. Then later on, there's a sort of correction. If this were possible, it would mean, well, you don't need to bother with the correction phase of quantum teleportation. So this represents an impossible algorithm, and indeed, this has no solution to Hilbert spaces.
So this has to be intended as an elevation.
Yes.
I mean, I'm a bit perplexed by the input side. They're not topologically equal.
Right, they're not topologically equal, but we're asking whether we can. So these blobs are unknowns, if you like. They're just say, I want to do something, some measurement here, some control operation here that would make this true. So just like any equation, we're now going to solve for it. We're going to say, well, can we find values for this which makes this true? And the answer is no, we cannot. If we could, then we could perform this, but it doesn't make any physical sense, so it's good. possible algorithms look perfectly reasonable. Okay. So this was shown by a student in our group, not to be possible, Brendan Fong, I don't think he's here, so he can't put his hand up and become famous. But let's unpack what this means. Well, we start with a quantum system. I think this is perfectly reasonable. Maybe someone here knows some reason why this is obviously not possible. If they do, that would be great to hear. We start with a quantum system. We then prepare 2 more qubits, which are entangled. We then prepare 2 more qubits, which are entangled. So we've got 5 qubits. Qubits 4 and 5 are measured in some bipartite basis. Qubits 1 and 2 are measured in some bipartite basis. So we're just left with qubit 3. We then do something to qubit 3, depending on the value, depending on the results of our measurements of qubit 1 and 2. I keep saying qubits, but these could be arbitrary quantum systems. We do something to qubit 3 depending on the outcome of our measurement of systems 1 and 2. And then we do something to qubit 3 depending on the outcome of the measurement on systems 4 and 5. And as a result of that, our quantum system has been teleported in a sort of generalized sense. It's been left completely unchanged. And the classical information is just in some sort of uniform distribution. So I call this interlaced teleportation because it's sort of like performing 2 simultaneous quantum teleportation experiments on the same quantum system where you take turns in doing it. I do my measurement, you do your measurement, I do my control operation, you do your control operation. But it's impossible. Why is it impossible? I mean, we have a proof, but I don't have an intuitive understanding of why it's impossible. But whatever the reason is, it must be topological. And that's because implementability, in this sense, these formal algorithms, is a topological property. If I do some crazy deformation, then that will preserve implementability. So by definition, straightforwardly, questions of implementability are topological invariants. Okay, what about possible algorithms? Maybe I should run this first. Well, this is quantum teleportation. So what happens here, we should go hands at this now, we've got a quantum system. We prepare qubits, let's say qubits now, qubits 2 and 3 in the Bell state. We do some bipartite measurement of qubits 1 and 2. And depending on the outcome of that measurement, we perform a control operation on qubit 3. It's certainly not true that every such way to do that yields a successful quantum teleportation algorithm being invoked, but certainly it is possible to do those things such that this holds. Therefore, this has a solution. In fact, it has many solutions because there are many bases here that you can choose and corresponding controlled operations you can perform, which yields a successfully teleported quantum system. So, I don't know, Dan, just looking at this, answer your question about the sort of scope of the classical information somehow.
Right.
So here we're performing our measurement, we're getting some classical information. This is where it lives. This is sort of the future cone of where in space-time the result of this measurement is, and we can make use of it if we like by allowing some other quantum system to sort of move into proximity with another quantum system here, which is correlated with this classical information because it bounds this classical information. That's the idea. Now topologically, we can sort of move this around. It's just the same as this. And implementability, as we've discussed, is a topological invariant. So instead of drawing this picture, which is a bit more complicated, we can just draw this picture, which is much simpler. So this is what I mean by the fact that this picture encodes quantum teleportation. And in this way, you can take some algorithm which might look a bit messy when you lay it out like this in ways that exactly correspond to the steps that we need to perform. But then when you rearrange it topologically, it's looking beautiful.
What does it mean in the transition from the first equation to the second equation? You've changed the boundary.
Yes, I've done that. That's fine.
That doesn't correspond with going back in time on your information.
Oh, probably. It's fine. We're happy with going back in time, aren't we?
Is that really an implementation invariant? I mean, is implementation really a topological invariant in the sense that in one instance you might be going back in time and in another you wouldn't?
Yes. So, verbatim, this says we start with some piece of classical information, and then based on that piece of classical information, we do something to our quantum system, and then we do it again. And actually there are some slightly tighter restrictions than on the solutions that I've been able to explain so far, but the point is that these two things, performing two control operations one after the other, just analogous to performing this measurement within a single control operation. Okay, so there are also novel implementable algorithms that we described using this framework. Still, we're not really using the framework for anything more than a pretty way to talk about these protocols. Nothing that we've talked about so far could be described or proved or disproved using ordinary ways of describing, working with protocols. But somehow having this language available allows you to very quickly just draw little sketches and think, well, could that be quantum algorithm? What does that picture mean? So this is three-stage teleportation. And the idea is that we just look at quantum teleportation and say, well, look, there are two things. What if there are three things? What does this mean? Does this make any sense? And so we get this pair of diagrams, and of course we can stretch these around however we like. So what does this mean? This is an algorithm in which, instead of doing two things, a measurement and a control operation, as in teleportation, we do three things. And the result of those three things is that the system will teleport successfully. And this is possible. There is a solution for this. And the basis that you measure in isn't the Pauli basis, which is a basis of unitaries, which all square to 1. It's some other funny basis that I invented, which is a basis of unitaries which cube to 1. And it turns out that such a thing is possible, and constructed in quite a pretty way, involving a tetrahedron living inside blocks. So this is an example of the sort of thing that you can talk about quite easily using this formalism. Okay, so now I want to step back a bit and try to approach from a completely different direction. So what's going on here? Trying to convince you that it's possible that all this stuff is doing what it says on the tin, right? Because otherwise it just seems like this sort of swanky thing with all these pictures, which is a bit Deus Ex Machina. Anyway, so let's suppose we begin with some pure state, phi, an element of some coordinate space H. Now, if you've heard talks about category theory and quantum mechanics before, then maybe you've got the idea that you can see this as living in the category of Hilbert spaces and linear maps. Great place to study this. But now what happens if we perform a measurement? Let's just say it's a two-outcome measurement. Well then, depending on the outcome, we'll have two possible states. If P1 and P2 are our projectors corresponding to the measurement outcomes, then either our state is P1 phi, not worrying about normalization, or our state is P2 phi. So if we want a complete analysis of our whole protocol, we've still got to hang on to these two possibilities after this sort of branching that's occurred as a result of the measurement. And so these live in H plus H. We've now got two copies of our Hilbert space. And maybe more things now happen in our quantum protocol. But we can't do arbitrary things now. We can't apply unitaries which mix up these copies of H, for example. That wouldn't make any sense. Because these are now supposed to be separate universes, if you like, separate worlds which have been created after the sort of measurements being performed. As we're analysing our protocol, it wouldn't make any sense to apply a unitary which just swaps the states over between the factors of the direct sum, for example. So really, we're not living in the category of Hilbert spaces anymore. We're living in some very slightly more complicated world, but still pretty basic, which is just two copies of the category of Hilbert spaces. Right? Because we've got two Hilbert spaces, each with some state, and if we're going to perform some sort of unitary dynamics, well that's just some unitary dynamics on the first copy and some unitary dynamics on the second, not allowing any unitary dynamics to cross things over. So the point is, this is just the category of Hilbert spaces we should be interested in if we want to model quantum algorithms. We should also be interested, for example, in two copies of the category of Hilbert spaces, which is a different category. Dramatically different, but it's a different category. And in general, you know, we'll need, of course, n copies of the category of Hilbert spaces. But these things have been well studied and turned out to be surprisingly important in, say, representation theory and higher algebra, and over in the Maths Institute, for example, people love these categories. They call them two Hilbert spaces or two vector spaces. And if you want to study them, if you want to work in a setting where they're all together and available for you to use formally, well then they form a two category, they don't form a category. Because categories are things that contain things made out of sets. But these are categories, so they need to live in a two category to give you space to work with all of their features. But this is just this two category that we could form, where the objects are just n-fold copies of the category of Hilbert spaces. Well, that's just the category of two Hilbert spaces which I described earlier. This is exactly our target category in which we're trying to find solutions for our formal algorithms. And in fact, I want to say something very strong, which is that two Hilbert spaces are really fundamental. They really need to be taken seriously. Now, when I say this to people, a common objection is, well, come on, it's the Hilbert spaces that are important, right? All you've done is you've taken copies of the category Hilbert spaces and stuffed them all together and said you've got some new profound thing. Obviously, it's the underlying Hilbert spaces that are the important thing. This is just something we've done on top. But I could say just the same thing to you about Hilbert spaces. Hilbert spaces is just a bunch of complex numbers stuffed together, right? Suppose you've got some linear map between two finite dimensional Hilbert spaces. Let's just make sure it's a complex numbers. Like I say, it's the complex numbers that are important. These are the quantum amplitudes for things to happen. These Hilbert spaces are just stupid mathematical abstractions. It's the amplitude which are really important. And I guess I could say that, and you would agree with that. Or not agree with it. I expect you wouldn't agree with it. But my point is, it's just the same thing going on here. Just as a Hilbert space, finite dimensional Hilbert space is of the form C to the n, some finite n. So every two Hilbert spaces is of the form Hilbert to the n. And just as Hilbert spaces are important as ways to collect complex numbers together, so two Hilbert spaces are important as ways to collect copies of the category of Hilbert spaces together. So I'm doing remarkably well for time, so I'm just going to talk quickly about the sorts of things that I want to do with this and the sorts of things I think we can touch upon. So we've talked about implementability and how it's a topological invariant by definition of these formal algorithms. But then we can ask, well, can we compute it directly? So this impossible algorithm that we saw, like interlace teleportation, is there some topological feature that we can compute with the diagram that defined it? Let us conclude immediately that this is impossible. I suspect there are interesting things one can say along those lines. So then the idea is, if someone has an idea for some new algorithm, they could draw a picture of it based on the specification of how they want the algorithm to operate, and then we look at the topology of those pictures and compute some invariants and say, no, that's not possible, no, yes, that is possible. But the impossible algorithms, why are they impossible? Because the proofs of impossibility we've got are a bit opaque. Not to say that they're complicated, but they're not particularly enlightening. Whenever you've got something that seems rather basic to describe, it doesn't seem obviously impossible. I mean, if it is impossible, then you need to ask, why is it impossible? What's this tell us about quantum mechanics? What if we lived in some world where this was possible? Would this change our whole universe? I mean, who knows? Can we find a broader class, interesting class, of novel implementable protocols? So we can draw all these pictures, right? There's almost too much stuff to go for. Any picture that you can draw with these regions and lines and vertices could be interpreted as some sort of protocol. Which of these are interesting? Which of these can be implemented? And if you can find a broad class that can actually be physically implemented, how can they be implemented in the lab? How do those sorts of practical considerations include the topology of these pictures that you draw? I'm also concerned about more general sorts of algorithms. So the algorithms that I compute very well in this framework are things like teleportation, entanglement swapping, dense coding. What else do I want to say? Well, anyway, there are a broad class of existing algorithms which fit really nicely into this picture, but some which don't. So we've got JOSA algorithms, algorithms which are sort of heuristic or probabilistic, which are still very important algorithms, but just don't fit so neatly into this sort of topological worldview. So this is something that Bob is interested in as well, the question of how to treat these sorts of algorithms which historically don't fit so well into this sort of categorical framework. And sort of connecting to that, leading from that question, I'm also interested in investigating connections with other sort of areas of mathematics, and in particular group representation theory fits beautifully into this world of two Hilbert spaces. In fact, one of the earliest important theorems in category theory was proved by physicists, and it was a proof about the representation theory of finite groups. They were interested in that because of particle physics. If you've got some theory of particles that knows some gauge group, then representation theory is very important because group representations are your particles. and intertwiners between representations are just interactions between the particles. And there's a very profound theorem called the Dr. theorem, which turns out in modern language to all be about two Hilbert spaces. So the point is, you can work with group theory in a very powerful way in this setting. And we know that there's a lot of group theory underlying these interesting algorithms, like Shor's algorithm, Deutsch-Jozef, and so on. There's a bit of a nebulous connection, but I think that's some evidence that there's some interesting stuff to be done here. There are very rich models of logical ideas in this setting, classical logic, linear logic, and their interaction. You can talk about combinatorics in a very interesting way in this setting. And also topological quantum computing, in some sense, this is also the natural place to talk about that. People use two Hilbert spaces all the time to talk about topological quantum computing. And sorts of pictures that people draw there are really just special cases of this sort of pictures that would be I've enjoyed this talk. So that's it.
Questions?
In a rich protocol with many players, many qubits, and much classical data being constructed, will 2 dimensions be sufficient to draw such
No, probably not. And actually, there's absolutely no restriction to 2 dimensions. So these things, as it happens, all the examples I wanted to give sort of float on the, seem to sort of be on the page quite nicely on the plane. But in fact, things can float on top of each
So
other.
I want to ask, what's the correct space for,
It's 4 dimensions.
and that's to do with the 4 dimensions of space-time?
Who knows? It's the same. It's the same 4. And people wax lyrical about the deep, profound things going on there. And there are certainly very deep connections between higher category theory and your ability to draw knots in space-time. And it just so happens that the level that we need to go here, which is 4, is the same as the level of our universe. Who knows if that is an important fact?
My question is sort of related to my earlier question and also to this one. Can you explain again why is the line representing a quantum system, is that right?
Yes, that's right. All lines represent.
I'd like to understand why is that the boundary of classical information? That's something I don't understand, this connection. Why is it the boundary?
So here we're forming a measurement. So we start with a single quantum system. There's no classical information, no correlation, just a quantum system, just a Hilbert space. Then after that, we've got 2 quantum systems, and their states are correlated. That is, for any value of the classical information, you could give me, for any value of classical information, I'd give you a pair of projectors. Such that if you know the value of the classical information, then you know that the joint state of these 2 systems is P1 times P2.
So another way of interpreting that is entanglement between those.
Oh, absolutely, yes. So the point is, where is our classical information? What is classical information? You give many answers to that. In this setting, it's nothing but the correlations, entanglement between more than one quantum system. In particular, that's why we start with 1 quantum system, then we end up with 2.
Surely it's significant that the coloured regions here are classical correlations and the white regions where you've used them quantum correlations.
Right, so there's no fundamental difference of type between the coloured regions and the uncoloured regions. The uncoloured regions just mean trivial classical information. If you've got some quantum system and you're extracting trivial information from it, then...
What I mean is, in the picture where you had a loop that went like that, you said that when the region above it was blank...
This one maybe?
Yeah, when the region above it is blank, that refers to a bell pair, but when the region above it is coloured, that refers to creation of uniform classical data.
Right, so
Now, the creation of uniform classical data is a different physical process from creation of an entangled bell pair.
Right, so that's true. So here, this is quantum teleportation in the ordinary set fashion. Here, we're creating 2 quantum systems out of nothing. And there's no classical information around, at least at this stage of the protocol. And certainly they are correlated, they're entangled. But they're not correlated or entangled, they're not correlated with respect. I'm not sure how to say that.
I think the way to see it is to ask what colour would be the correct boundary of the diagram, because that's going to correspond to correlations that aren't contained within solve the lines on the diagram.
So certainly if you have, as you do here, some classical information which hits the side boundaries of the diagram, that means that the value of that classical information is totally fixed. It can't be messed with. Because as it were, this quantum system is correlated with respect to the value of that classical information. It's correlated with some other system that's just sort of off the page, that technically draw. So we're not going to be able to mess with the value of that piece of classical information because it's encoded by something we can access.
Yeah, so that's my point. That the line on the right of the right side of that equation is very different
So
from
this
the one
one-
on the left, because one's pure state and the other isn't. So the colour is having a significant.
So you could be in the church of the larger Hilbert space and you could say, well, it is pure just with respect to some other quantum system that we're not considering.
It on its own.
Or
is-
you could say it on its own if we only talk about things that we can access in this picture is in some.
The point is that the colour is clearly changing what's
Absolutely.
going on in the picture. Yeah.
So I want to ask you some questions about the topological aspects of this. So what's your definition of continuous transformation in this picture?
Okay, so that's maybe a bit blasé about, but the idea is, if we go back to my slide, the idea is a one-parameter family of such diagrams which is smooth and which contains and such that at every point in this one-parameter family, none of these geometrical objects intersect each other or do anything nasty. So I think it's the intuitive notion of smooth deformation in the picture, and one can make that as precise as one likes, probably in different ways.
But the interpretation of these diagrams as like time flows upwards, right? But like if you rotate them,
Sure, no, yeah, you can do that.
in the measurement picture, you get the horizontal.
Yeah. So the interpretation would become totally different. I mean, if you wanted, you could grab the middle of this picture and you could twist it around 360 degrees, 720 degrees, 1,000 degrees. You keep twisting, and you get something that looks bizarre, but still be a perfectly implementable protocol. It's not complicated to perform, but it would encode just the same flow of quantum information as this.
I don't see how you interpret it like the rotate is. If you rotate the vertical line horizontally, if it has a different physical interpretation,
Sure.
how can you say it's still implementable if I don't even know how to?
Simply, well, so the answer is just as simple as suppose we do have an implementation. Then in particular we just have a whole load of linear maps and so on, which tell us what we mean by performing these measurements and so on. The mathematics that lets us twist these around, we can use the same mathematics to take our linear maps and just twist them around in a similar way.
Reverse it.
Yeah.
But there were diagrams you couldn't implement, so that means that there's no...
Right, and so similarly there, if you've got an impossible algorithm, no matter of however you deform that, it could just be some other much more complicated impossible.
Do you have any examples that, like, all the examples you gave looked like they were line Schmidt decomposition? You know, they're all kind of bipartite combinations of things. Like, I'd like to see something for which I could see that G of Z is different to W or something.
Yeah, but let's talk about that sort of thing because I'm interested. I don't have any great instant answers, but yeah, that's exactly the right sort of thing to be asking them.
The next one.
So is this implementability and possibility thing a topological criterion that you can use?
Yes.
So what is it?
Oh, I don't know. That's why I was on the path side.
Ross. Maybe related to Terry's question, what would it look like in this notation here, again, two controls?
So that would be the sort of situation where you need a sort of you have to go out of the page and you need to be a bit non-planar. So you'd have, that isn't red, what are these doing?
Behind you.
Yeah, great. So you'd have one piece of classical information. There it is. Then you'd have some other piece of classical information. Some other piece of classical information here that doesn't ring, just so we tell the difference. And one's floating on top of the other, but that's fine, they're not interfering with each other. And then we have our quantum system. And then we just have some interaction that would involve all three of these vertical black lines, which are the three quantum systems. One of which is correlated with this green information, one of which is correlated with this red information, and one of which is not correlated.
Okay, well maybe we should move on, save more questions for the break. Thank Janie again.